mirror displays, and we'll just leave it that way, and that'll be just fine. Okay, so there's my messy desktop. Okay, so since I didn't know what to talk about tonight, I figured I would leave it up to you. So I have two basic topics that I was going between. One would be a little bit about the JIT compiler inside the hotspot engine, and the other would be about garbage collection. So, choice is yours. What would you like to hear? Okay, hands for one. Okay, so we'll do hands. Okay, first off, JIT, hands up. That's just-in-time compiler. Garbage collection, hands up. You said JIT? Okay, who said that's a just-in-time compiler? Okay, just-in-time compiler, hands up. That's a hotspot engine. We have 1, 2. And garbage collection. Garbage collection. That's 1, 2, 3. Okay, garbage collection it is. Excellent. Okay, so I'm going to do garbage collection. Okay, so we'll talk about GC. So instead of doing those slides, I'm going to do some of these slides. And it's a good thing too, because the customer just sent me a garbage collection log, and so we can look at it live here. Let's see what we have here. What is this? Oops, what happened here? Something happened here. Oh, weird. Okay, let me start. Here we are. Okay, so in this case, I'm going to try to focus on tuning. Look at that. The slides are all cut off. Okay, tuning the G1 GC. And the reason why I want to, I'm going to have to fix this also because the screen is bad. Arrangement, display, optimized for Perl HTML for built-in Retina. No, standard. Nope, it's not going to let me do it because of the. Oh, excellent. Okay, so we have a problem here, and I don't have Steve to help me, but I'll work around it. That's fine. Okay, so so the reason why I want to focus on G1 GC is because in Java 9, this will become the default collector, so so the question is, how do you tune the G1 GC garbage collector? Well, you set the max heap size. We all know how to do that, right? That's minus mx set of size. We're good. And if you don't want to set it, it'll just take a quarter of physical RAM, and that'll be your default heap size. And then you set a pause time goal, right? And this is basically what's the longest pause time you can tolerate. And in this case, the default is 200 milliseconds. And we're done, yes? That's it. That's all you have to do. That's all you have to know about G1 GC to tune it. Any questions? No questions? You can ask a question, yes. Does that work for all? That's a very, very good question. This is a general does this work for all applications, all the tuning strategy? Well, for those of you who can't read it, it says, I lift, you grab. Was that concept just a little too complex, Carl? Right? Okay. And you can see there's our bears pulling up the igloo to get the Eskimo who's running off. Okay, and the answer to that, if only it were that easy. So, no, that's not a strategy that works, and this is why I had the customer just send me a GC log, because I've been trying to tune their entire cluster of 1,500 JVMs. And they have them segregated in services so we can do them bundles at a time. But essentially, we've been working for almost the last year trying to stabilize the garbage collectors. And then once we got them stabilized, they said, okay, Java 9, we're getting G1 GC. Let's see how it works. So let's redo the entire exercise. Instead of with the mostly concurrent collector, we're going to do with the G1 GC collector. Are you guys familiar with the mostly concurrent mark sweep collectors, the garbage collector? Anyone try to tune garbage collectors? Okay. I think we're talking about late night comatose here. Everybody, hands up. Both hands up. You're under arrest. Okay. Okay, great. Now, everybody who doesn't know anything about any garbage collection, put your hands down now. Oh, that's not so bad. Okay, there's a few. Okay, excellent. CMS, hands up again. Okay, so we know their arms are working, so I can trust the answer here. That's good. Okay, so what we want to do, so essentially what we're saying is, like, before we'd use the mostly concurrent mark sweep collector, if we had pause time concerns in our application, so you've heard about the new JE stuff that's coming down the line, right? And in those environments, we generally are worried about garbage collection pauses. And so we use the mostly concurrent collector in those environments to try to minimize the pause times. And the only issue with that particular technology is that it simply doesn't scale up to larger and larger heap sizes. So as you use larger and larger data sets, your pause times are going to go up and up and up, because the pause times are going to be dominated by the amount of data that you retain in heap, and partially by the overall size of heap. So effectively, what we needed was a new garbage collector that would allow us to scale up to larger and larger data sets and larger heaps, and the G1 GC is just that garbage collector for Java 9. Right. So the question is, what impact will this have on your application's performance? Right? When should I care about garbage collection tuning? And if I care about it, how am I going to tune this? Now, unfortunately, we don't have enough time to cover all of these topics tonight, but I just want to give you some familiarity with the G1 GC so that you can start looking at it and try to figure out what's going on, right? So really what we're saying is that, this is another collector. It offers us different scalability factors. It's going to impact the performance of your system. Sometimes it'll be good, sometimes it'll be bad. It's hard to predict up front. And, it's something that you're going to have to deal with in the future, because this will be the default collector. The default collector today is actually the parallel collectors. So I'm just going to go down to actually figure out, okay, what does this thing actually look like? So I'm going to put this diagram up here. So here's a diagram that we, I'm sorry, with the lighting it's a little difficult, but this is a diagram that we actually drew with an FX application, drawing on data from a live production system. And what you're going to see is that we have one contiguous memory space that's carved out of Java Heap, right? So we'll malloc this and reserve this space here. And then I'm going to divide it into approximately 2,048 different regions. And these regions are going to be either 1 megabyte, 2 megabytes, 4 megabytes, 8 megabytes, 16 megabytes, or 32 megabytes in size. So it's just going to do some math and figure out what the appropriate size should be. And it's going to take all of these regions and it's going to drop them onto a free list. Okay? Now, this is going to have some generational properties in it, in the sense that you can see down here, we got some green regions strung out down here, which are known as Eden regions. I have some yellow regions here, which are known as survivor regions. I have these blue regions, which are tenured regions. And we end up with these two color here, which is like humongous regions. So if you happen to be using JSON, like David has suggested that you should be using, then you're probably going to find you're going to be bothered by these things here, which are called humongous allocations. So consider it this way, right? Say you have an object that you serialize into a JSON string that happens to be, I don't know, like a little bit more than a megabyte in size. That's not uncommon. We can see that happening. If your region size is only 1 meg, that means the bucket isn't big enough to hold all of the data. So what do? Well, in this case, what we have to do is we have to find a couple of regions that are contiguous, string them together, and then you can allocate the JSON string right into those buckets, okay? Now, as it turns out, this is one of the things that really disturbs the G1 collector. It does not like humongous allocations all that much. They've been doing a lot of work to try to make it a little bit more large object friendly, but you know, we still run into these issues. And you can see with this thing here, we have lots of coral, lots of orange, and that's the thing that was disturbing the garbage collector in this particular case, is that we just have a lot of this humongous allocations taking place. Okay, so yeah, so you can see that, so what's going to happen at the beginning of the cycle, right? At the beginning of the cycle, the VM is going to say, okay, you get, I don't know, 1,000 regions. And then as you start allocating, so you're going to go new, right? New object. What you're going to do is you're going to pull a region off of the free region list, and then you're just going to start allocating in it. And when you get it to a certain level of fullness, you'll just go back to the free region list, you'll grab another one, you'll fill it, grab, fill, till you hit the 1,000 limit. When you hit the 1,000 limit, then what you're going to do is you're going to invoke a young generational collection. And the young generational collection is going to look after all the green bits, and it's going to look after the yellow bits. Okay? So this collection is going to be stop the world. In other words, we need to take all of the application threads, bring them to what's known as a safe point so that they're not functioning anymore. And we're going to do this modal switch into garbage collection mode, where the garbage collection threads are now going to start working. And what they're going to do is go through what's known as a mark sweep. Okay? And the sweep in this case is going to be an evacuation sweep. So what we're going to do is, as we mark, we're going to find all of the live data, right, by tracing the pointers. And then when we sweep, we're going to take everything that we've marked live, and we're going to copy that into new regions. In particular, the Eden data is going to go into the survivor regions. Okay? And as we sweep the survivor regions, we're going to decide, do we keep the data in the survivor region, or do we push it up into the tenured region up here? So there's going to be a flow of data through this particular system, and the flow is going to go from green to yellow to blue. Unless, of course, you're humongous. If you're humongous, then you're just going to be put up into this region here called the tenured region automatically. Okay? So that's the flow of data through the system. Now you can think about, okay, well, so what are the things that are going to bother all of this? Well, the first thing we have to do is we have to engage in this activity known as a scan for roots. So if I'm going to trace pointers, I need to find the root pointer. And the root pointer is my starting point. So I need to scan all of the spaces, and I need to find all of the roots. And that's going to give me my starting point. And then what I'm going to do is I'm going to start the collection from there. Okay? So I have to do a scan for roots. Then I have to do a mark. And then, of course, I have to do the evacuation. And the evacuation is a copy operation. And that's pretty much everything that happens here. So that looks after young generational space. So the question is, like, okay, so what happens up here? Well, this is something completely different. Well, it's the same thing, but different, I would say. So what happens here is that I'm going to allow this to expand and expand and expand, and until it takes approximately 45% of heap space. When it hits the 45% threshold, what I'm going to do is I'm going to trigger a mark of all of these things here. And the mark, what it's going to do is it's going to just mark all of the live data, and it's going to calculate the occupancy, live occupancy, for each of the regions in this particular space. Now, when the young generational collection runs again, it's going to collect all of these, and it's going to pick up some of these, and it's going to sweep these, the combination, right, in what's known as a mixed collection. Okay, so young will build what's known as a C set, or a collection set, automatically. The green goes in, the yellow go in, and some of the blue go in. So how do I decide on which blue go in? Well, in order to decide on which blue are going to go in, I'm going to use the pause time goal. So I'm going to do an estimate of how long it's going to take to collect this. And then I'm going to fill the pause time goal by looking at how much is live in each of the regions, and then picking regions, I'm going to pick the regions until I fill up the pause time goal. So part of what I'm going to do is I'm going to sort these things by occupancy. And you can do a little guess, right? How long does it take to collect an empty region? 0. Yeah, we got it. Awesome. Okay, you get a sticker for that one, right? How long does it take to collect a free region, like a completely full region? Well, it takes a long time. So we're going to have a cutoff that says that 85%, if you're more than 85% full, that's expensive. Don't do that. If it's less than 85%, we're going to say that's cheaper, do those ones. And that's how we're going to decide. We're going to sort them by how full they are and just chunk them up to 8 different mixed collections in a row to basically clean out all of this particular space here. Does that make sense? Okay, now we get a problem. The problem is with the root set. Where are the GC roots? Well, in garbage collection lingo, GC roots are these things known as external pointers. An external pointer is a pointer where if we have foo pointing to bar, if foo is in the other room and bar is here, then foo is an external pointer to bar. If they're both in the same room, foo is here and bar is in the same room, then that's known as an internal pointer. We need to find all of the external pointers. So if I pick a region here, like maybe that one there, the question is, where are all of the external pointers? Well, they're here. And you're going like, that should basically go like, oh my God, now we have a problem. I need to scan all of this to find what's in here pointing to in there. And then I need to repeat it for every other region that I'm considering. And it's, okay, that doesn't sound like a good thing, right? So how are we going to fix that? Well, we're actually going to build these things called remembered sets. So I'm just going to go all the way down here to where the remembered sets are. And what the remembered sets are going to do is they're going to say, like, if I have an external pointer, I'm going to record that information in a form of a card table. Okay? And so to find all of the external pointers for this particular region, I just need to go to its remembered set, and the remembered set will actually pick up that information, will have that information. So I can just get all the pointers by basically doing some work with this particular data structure out here. Now, that means that every time you mutate an object that's in tenured, like if I have foo going to bar 0, and then I say foo now goes to bar 1, that's a mutation. And basically we have this fight against who does the work. Do we push the work onto the garbage collector to keep everything clean? Or do we push the work onto the allocators to keep everything clean? And in this case, we need to strike a balance. So we don't want the allocators updating the RSet, because that's an expensive operation. So what I'm going to do is I'm going to enqueue that information into an RSet queue. And it's going to be zoned so that as it gets full, as you do more frequent mutations, what I'm going to do is I'm going to more aggressively try to clear that out. Because if I don't have that completely cleared out before the garbage collector has to run, then the garbage collector is going to be responsible for clearing it. Okay? So that's, so what we're going to do is, like, we're just going to say, oh, let's keep a remembered set, all right, for, for every inter-region, every time we have inter-region pointers. So we're just going to remember that. But that's only from tenured into young gen. That's the only place where we need it. We don't need it actually in young gen, because we're always going to throw all of those regions into the collection set. Right? And so this is really the really super fast explanation as to how it all works. Is there anything else that I want to say in here? No, that's not. Let's look at a GC log then. Okay, so there's some directions in here as to how to get a GC log. And what I've actually done is I've been working for I don't know how many years on tooling that does, and we have a company in London that actually does a whole bunch of different, it takes information from the GC log, and I can fix this now, can't I? Excuse me. Okay, so we can take information from the GC log and we can actually use it to figure out what's going on. So this person is complaining that there's some issues, some problems, and they don't know exactly what's going on. So traditionally what we've done is we've built some charts that look like that. Isn't that nice looking? Okay. And so what are we saying, right? This is the occupancy of the heap after the collection has run. Right? So that's one of the charts we might look at. Well, if you're looking at charts like this, you might go like, oh my God, I don't know what's going on here. This is a real mess. Right? You can't really, it's noise. It's awful. Okay. So what do we want to do instead? Well, we like analytics. The reason why we like analytics is because I can get algorithms to see things that are very difficult for me to understand. Like we have one right here. So we have a whole bunch of different analytics here, and we have this one here, which is called heap too small indicators. And we can see this, right? There are 31 GC events out of 45,000 that indicate that a heap was too small, or there's an internal memory pool that's too small. So since Eden is different than tenured, which is different than survivor spaces, each of these spaces has to be appropriately sized individually. And once you know what the appropriate sizes are with a couple of other figures, then you know how big you can make heap. That's how we're going to decide how to make the size of heap, right? In this case, we're getting 2 space overflow events. Now, the 2 space is another name for the survivor space. And because we're getting 2 space overflow events, that means the survivor space is too small. So we need to do some configuration to try to minimize the impact. And we actually have premature promotion. So this is the JVM trying to protect that buffer from buffer overruns. It's taking data and pushing it up into tenured space before it should be in tenured space. If that makes sense to you, right? So this is another indicator that we have some problems in the internal configurations of our heap. Here's our premature promotion. And a consequence of that is we're going to have high pause time. So this is like a 8.6 second pause time, right? Which is quite a long time. Not as long as it used to be for this app, but it's still quite bad. So we can look at this information. Now we can come back and we can see, okay, what's happening. Well, we see heap after GC, which is a quite nice indicator. So it looks like, now we can start breaking this. It looks like the live set is pretty stable, and it's about 1.4 gigabytes. There's only about 1.4 gigabyte of data live in this heap. So, that doesn't seem too bad. We have like a 7.2 gigabyte heap, excuse my bad math. But I like to look at things a little differently. In other words, I find that what's happening in tenured space is really going to be a predictor of what's happening with the pause time. So I'm going to break it down. I'm going to say, okay, so what does tenured space look like? And you can see the red bouncing around is like the JVM resizing the heap space all the time by giving it different numbers of regions that it can use. But essentially, you can see there's our 1.4 gig sitting in tenured space, and you can see that quite often, it's just basically pushing the heap size down to the point where it's running the collector much more frequently than it should be. And yeah, sure. Oh yeah, so you can see a little easier. Yeah, I'm sorry for the yeah. Then we get pushed up into this one here, which is a little problem, right? So we can start looking at characteristics, but there's another issue here. It's like if the young space is too small, then the survivor space will be too small, because survivor is built into the young generational space. And we can come down here and I can look at memory pool sizes, and you can see indeed most of the time the young space is shrunk down to a really small size, and that creates a whole host of other problems. So in this case, there's a parameter that says, you know, let young shrink down to 5% of heap. So what we might want to do in this case is say, no, we don't want it to go to 5%. Maybe we want it to only get down to 25%. And maybe that'll cure the problems that we're having with the survivor space being too small. So that would be the simple thing that we would do to start tuning the garbage collector. Now, I'm not sure exactly how much more time I can really take here about the whole thing, but you know, there's other things we can actually look at to see what's going on. There's other indicators in here. For instance, we have the ability to detect noisy neighbors if you're running in server environments. We can tell you if your server is misconfigured by basically looking at this view here and running some analytics over it. Okay, and there's a bunch of other things that we can find. But really, in order to, oh yeah, so we can look at, here's the G1 young generational phases. And you can see there's parallel phase, which is the dominant phase here. Actually, if I do it as a percent, it looks even better. So the parallel phase is dominant, which is good. And then we have some other phases that you can probably see on the screens there, like a code cleanup, other, right? Code root purge. So these are all of the internal phases for the garbage collector that I don't really have time to talk about here. So if I look at the parallel phase, you can see that I have a lot of object copy here, but I have a lot of rset update time. Now the rset update problem might be related to the young generational space being too small. So by not allowing it to shrink as much, we might calm that down, but it might be that we're not aggressive enough in cleaning up the queue, so we're leaving too much work behind, right? This should really be no more than 10%, but if you look at that blue strand, the blue strand strays up to 40% of the total time, okay? So anyways, you can see by getting these visualizations, what we can do is we can start figuring out what's gone wrong with the garbage collector, and then we can use this information to adapt the garbage collector to better meet our application. In the cases of where you have just lots of humongous allocations and these things happening, then what you want to do in those cases, you want to go in and change your application, right? We have some other things happening here, like if I go to allocation rates as an example. So if we look at the allocation rates here, we can see the allocation rates in this case are quite nice in my books. They're mostly below 700 megabytes per second. That's okay. That's an okay allocation rate. If the allocation rates were higher, then again, we'd have to tune the application for memory efficiency. And that would be an indicator that that's going to give us the best performance benefits, and also it'll also calm the garbage collector down a bit. Okay, and I would say that if you have a high allocation rate, trying to tune the garbage collector to fix it, it's not going to work. It's simply, that's the wrong direction to go in. If you have an allocation problem, you need to make the application more memory efficient. If you have a garbage collection problem, then you can fix the garbage collector to make the garbage collector more efficient. Right. So one of the things that bugs the G1, here's a benchmark that I was running and working on and stuff like that. And you can see by the chart that the runtime conditions really don't matter that much. What you can see is that CMS performed very well. Smaller is better in this case. And the G1, no matter what we tried to do to get it to perform as well as CMS, we just simply couldn't without using a lot more hardware. The only thing we can do is do this G1 new size percent, set that up to 20%. So we didn't let young gen shrink as much. And the reason why this works is because, I don't know if you've seen this curve here, it's known as the weak generational hypothesis. What the weak generational hypothesis says is that the longer data lives, the longer it will live. Okay? And most data is garbage collectible before it leaves the CPU. And that's what that curve represents. Now, there's another observation you can make in here. The area under the curve is the volume of live data you have in your system at any point in time. Yeah? It's a little bit of calculus here. And you can figure that out. And what that means is that that remains constant. So if object copy times, as we saw in our chart, was the dominant cost in the garbage collection, we can minimize the cost, not on a per collection basis, but we can minimize the cost over time by copying less, which means we have a frequency problem. If we reduce the number of times the garbage collector is running, then the amount of live data remains constant, that means we're going to incur the same cost over and over again, but we're going to incur it at less frequently. So overall, the cost will come down. And that's how we got the reduction or the improvement in performance by tuning the collector for the Cassandra benchmark. Okay. And that's probably all the time I have to talk tonight, but I'll certainly take any questions if you have any. Yes?
So you're talking about the allocation rate problem.
The allocation rate problem, yes.
How could you increase the memory allocation efficiency?
Okay, so that means you need to use a memory profiler on the code, find the allocation hotspots in the code, and then you're going to have to then change the algorithm or adapt the algorithm to try to reduce the allocation rate of your application. That will require a code change. There's no other way around it. You're going to have to change code.
Okay, I got it.
Okay. And he gets a sticker. He gets a sticker. These two get stickers. Any other questions? He gets a sticker. Yeah. He gets a sticker. Yeah. Yeah. Okay. Any other questions? You get a very nice sticker. All you have to do is ask a question. Could be as simple as, did you enjoy Fuji? No. Okay.
Sebastian,
You're up. Well, you should have been preparing while you get it. Yeah. So my commercial plug is visit our website at jclarity.com. There's trial versions of the software available for doing GC analysis, as well as instructions as to how to get the garbage collection logs. And we have an email list. Most of the world's top performance tuning experts are involved in the mailing list. And so we encourage people to join and communicate. We're setting up a Slack channel also for people to communicate with each other. So, yes, that's all I can say. Sorry? Performance tuning, yes. Can we expect performance improvements in Java 9? I think the guys have been doing a lot of work in making sure that the garbage collection runs better in Java 9 than it does in Java 8. Certainly you don't want to be doing any G1 work in Java 7. In terms of overall performance, I'm not sure that this is a build that there are going to be performance improvements. I'm not sure this is going to be a release based on performance. It's mostly going to be a release based on new exciting features that are coming into that are being put into the JVM. There's some work with finalization. I know everybody hates it, and we can have another discussion about that because it's anyways. So there's some cancelable there's operations that you can cancel that will replace finalization. So there's some of those things that are happening. Better native memory tracking so you can figure out what's going on. Off the top of my head, I'm having trouble remembering all of them. The collections are better, streams are better. We're getting a reactive framework that is going to actually possibly help with the performance in that. We've talked to them about fork join, which is basically parallel stream performance, and getting more controls on that so it's more useful in server environments. So there's basically bits of performance improvements coming from a whole pile of different directions. So, sorry? Okay. Yeah. So yeah, I expect that it will be more performant in most cases. It will be no worse than 8. And that's one thing for certain. Any other questions? Oh, okay. Yes.
It's probably a little bit off topic, but is it possible to employ those techniques you used to tune JVM, GC to other languages?
Yeah, the answer is okay. So if you're not running on a JVM, but running on like a memory managed environment, then there's going to be different options. The garbage collectors are going to work differently, but the fundamentals are going to be about the same. I think if you look at Go, they're using, well, they claim that they're better, but I don't believe it right yet. And they're using another form of garbage collector known as reference counting, and reference counting has its own issues, but they back up the reference counting with a mark sweep. Okay, so again, I think what you're going to see is that there's going to be a balance between allocators and the garbage collection or the memory management system, and how much work that you push on each side. And so my belief is in that in Go, you're going to get less of a GC pause, but you're going to get it at the cost of lower application throughput because you're going to put more work on the allocators to try to keep things clean, right? So they're marketing the hell out of better garbage collection, but they're basically very quiet about the other aspect of the equation. So maybe it's good for you, maybe not, right? So, I can't make that judgment here and now. Yeah. So I'm done. Thank you very much, guys. Bye.